Math 2414, Trigonometric Integrals, Integrating a Product of Secants and or Tangents, Part 1. If you've watched the first 5 videos and haven't totally lost your mind yet, then I have some good news. I'm going to take it down a notch in terms of insanity. Integrals of sines and cosines, really it all boils down to what moves work, which usually boils down to picking the correct substitution and using the correct identities to change the integral into something doable, whether it's a Pythagorean identity to replace unwanted trig functions with the trig functions you want, aka the trig functions equal to your substitution, or using power reducing formulas to knock down an even power to a smaller power which can wreak havoc afterwards. But you just got to say what is wrong and how do I fix it, and then just Hulk smash your way through the problem until you get to the end. And I'm not going to go as crazy with secants and tangents in terms of figuring out how to do things, but I do want to have some of that initial, how do I recover this information in case I forget it? Because honestly, when I integrate secants and tangents, I know there's a strategy for doing it, but I understand the strategy, so I don't have to memorize stuff. I just have to say what works and what doesn't work. Now, you may be wondering why secants and tangents lump together. It's because their derivatives are related to each other. Recall that the derivative with respect to x of tangent of x is equal to secant squared x, and the derivative with respect to x of secant of x is secant x tangent x. Those are derivative rules from Calculus 1 that I expect you to just flat out know. So anytime you're integrating a mess of tangents and secants, because their derivatives are related to each other, that's a suggestion that their integrals should be related to each other as well. But the trick here is making the correct substitution. If we're going to use the correct substitution, it's either got to be tangent or secant. The underlying premise is, what are we going to borrow for the du package, which is dictated by what we choose for u, but more importantly, is the stuff that's left over something we can work with. Let's consider the integral of tangent to the x, tangent fourth to the x, secant fourth to the x. Now some of you might be thinking, let me write this in terms of sines and cosines. Sine to the fourth over cosine to the fourth, 1 over cosine to the fourth. Trust me, it's usually going to do more harm than good. There's a good strategy for integrating tangents and secants, and I'll unveil that strategy shortly. But let's just jump into it and see what happens. Let's start by saying, let's try letting u equal tangent x. Let's see if that works. And if it works, great, we'll turn it into a technique. Well, if we choose this, and again, we're choosing this not knowing if it's going to work. I can't say this enough. You can't be afraid to try something, fail, learn from it, try something different. If we let u equal tangent x, then du would equal secant squared x dx. And I have enough pieces in my integrand, enough parts in my integrand to create this du package. I've got a dx and I've got plenty of secants. So let's just play with this and see if it works. We're going to leave the tangents alone for a second. Those are the trig functions I want because I'm going to call them u. I have 4 secants. I need to borrow 2 of them for this du package, so that leaves 2 of them behind. All right, let's take inventory. My du needs a secant squared to dx, which I have. So all this will become du. The trig functions I want are tangents. Those are going to become u's. So this will become u to the fourth. But what do I do with the secant squares? Those are my unwanted trig functions. If you recall, when we integrated sines and cosines, what we did with the unwanted trig functions is we used a Pythagorean identity to change them into the ones that we wanted. Well, I don't want secants, I want tangents. You see where this is going? We have a Pythagorean identity that says secant squared of x is equal to 1 plus tangent squared of x. So the commonality between this type of integral and the previous types is choose a substitution, find its du, build its du package, decide what you want. I want things that can do the substitution, and see what's unwanted and see if you can find an identity that changes it into what you want. Yep, I can change secant squared into 1 plus tangent squared. And that's good because I want tangents because I can call them u, which means that secant squared after becoming 1 plus tangent squared will become 1 plus u squared, since u is equal to tangent. At this point, I think you can see that this is just a matter of doing it now. We have the integral of u to the 4th times 1 plus u squared times du. That's the integral of a product. We don't integrate products unless we do integration by parts and change it to something else. But if you have a product and can get rid of it, do it. This is easy. I just have to distribute the u to the 4th to both halves of the addition problem. And I'm going to put it in highest to lowest power. U to the 4th times u to the 2nd is u to the 6th, plus u to the 4th times 1 is u to the 4th. That gets rid of the product, and now we can just integrate it term by term. So let's integrate it and change the u back to tangent. The integral of u to the 6th is 1/7 u to the 7th, so I will write 1/7 tangent to the 7th of x, since u is tangent, plus the integral of u to the 4th is 1/5 u to the 5th, but u is tangent of x, and so we'll write 1/5 tangent to the 5th of x, plus constant of integration, and it's over. Take the derivative, and I bet you can turn it back into that. Now, even though we got the answer, I'm not quite done with it yet, because this worked by choosing seemingly at random to try u is equal to tangent of x. So let's make note that that worked. But I also want to try the other substitution. What if u equals secant of x? Now, spoiler alert, it's going to fail, but I want to analyze why this one worked and the other one failed. I'll give you a hint. It has to do with whether or not you can change the unwanted trig functions into the wanted trig functions. So let's just keep track of this answer. 1/7 tangent to the 7th power of x plus 1/5 tangent to the 5th power of x plus c. And the substitution that we used, this was via, and if you don't know the word via, look it up. This was via u equal tangent x. But let's try it again. So we'll rewrite the problem here. But this time, let's try a different substitution. And I've already told you that it's going to crash and burn, but that's to figure out why it crashed and burned and see if we can develop a technique out of it. Let's try u equals secant. As we've already denoted, the derivative of secant is secant x tangent x. And we have enough tangents and secants to build this du package. So let's borrow what we need. We need to borrow a secant and a tangent to put with the dx, so each will go down by 1. Tangent cubed x, secant cubed x. We borrowed a secant and a tangent to package with the dx, so that we can take inventory of all 3 pieces of the du package. All this will become du. For this choice of substitution, our wanted trig function is secant, and here are some. So this will become u cubed, but this is our unwanted trig function. Do you see the problem? We have tangents, we want secants. And the identity, which I erased, the identity that allows us to change powers of secants to powers of tangents is secant squared x equals 1 plus tangent squared x. Or if we move the 1 over, remember you need to know variations of these trig identities. Anytime I have a tangent squared x, I can replace it with secant squared x minus 1, which is great because I want secants, I don't want tangents, but this tangent has an odd power. And because this tangent has an odd power, I cannot easily write it as tangent squared to some power. Don't get me wrong, I can. I can write it as tangent squared to the 3/2 power, but do you really think we want to go there? No. Because my unwanted trig function has an odd power, I'm not going to be able to push forward with this Pythagorean substitution because it requires having an even power. So let's see if we can figure out what in advance would have predicted that this was going to crash and burn. Angry face. If we choose u equals secant, we need an even number of tangents left to pull off the substitution, to get rid of the unwanted tangents using the Pythagorean identity. We needed this to be even, but we had borrowed one from it, so if it were even now, it would have been odd back here, and it wasn't. So this failed because the power of tangent was even. We would want it odd. Why did the other one succeed? It's gone, but the other one succeeded because if u was tangent, the du was secant squared, and so we had to borrow 2 of the secants for the du package, leaving 2 of them behind, which was great because 2 is even. So the reason tangent worked is because secant had an even power. When we borrowed 2 for the du package, it stayed even. So this one's not quite like the sine and cosine, because the sine and cosine, it was the same. Whichever one is odd, you let u be the other trig function. But without further ado, in fact, I think I'm going to end this video and then just start the next one with the technique. Yeah, it's a good idea.